Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. Today we shall begin our study with principle of transfinite induction. As a sample, we will also employ this one and prove Tikhonov's theorem. Of course, we have proved Tikhonov's theorem elsewhere, so that is a good way of learning a new tool. So test it on something which you already know where it works. Okay, so the principle of transfinite induction says the following. Start with a well-ordered set with a least element. We will denote it as 0. This is for convenience. Suppose P alpha is a statement about alpha inside X, and we use the symbol P suffix A to denote that P alpha holds for all points alpha inside A. A is a subset. Now, suppose P0 is true, and for any alpha inside X, P0 alpha, this is the segment consisting of all beta which is less than alpha inside X. So P of 0 alpha implies P alpha holds. Remember, this means that P of beta is true for all beta less than alpha. That is the meaning of P0 alpha. Then P alpha holds. If this is the case, then the principle of transfinite induction concludes that Px is true. That is, for all elements of X, the statement will be true. Suppose on the contrary, Px is not true. What does that mean? This just means that if you take elements inside X for which the statement is not true, that is a non-empty subset. This B is a non-empty subset. Okay. A non-empty subset in a well-ordered set has a minimum, okay, an infimum alpha, and alpha is inside this one. That is why we can call it as minimum. Since P0 is true, in the beginning I assumed P0 is true, and this implies this one, right? So P0 is always true. That means this alpha, which is the minimum, is not equal to 0, and moment is smaller than that, it must be true, otherwise alpha will not be infimum. So P of 0 alpha, this is true. Every beta less than alpha, P of beta is true. That is the meaning of this. Therefore, P alpha is true. Okay, that means what? Closed, if you can take, here you can take the closed segment 0 to alpha. Okay, but then what? Then alpha cannot be inside B. That is a contradiction. Oh, so that is the proof of principle of transfinite induction. which is, as you see, is an easy consequence of well ordering. Okay, so that is the whole idea. So within a well ordered thing, this always holds. The point is, you are already very familiar with the principle of mathematical induction. That is a special case of this, when x is the natural numbers along with the usual order. Of course, that is a well order. Okay. So this principle of transfinite induction is a far generalization of mathematical induction. This is true for any x. As soon as you have a well order there, you can use it like this. So our next aim is to illustrate the use of principle of transfinite induction with one single example, but that example is going to be something very important, namely product of arbitrary non-empty families of compact spaces is compact. Okay, that is a Tikhonov's theorem. We have given several proofs of that. Now we will give another proof of that one here. Okay, so this is again, here I am going to use one of the theorems that we prove in part 1. I won't have time to do that again here, but I will recall it for ready reference. This is the theorem that we proved in part 1. Let X be any topological space, then the following two conditions are equivalent. The first condition says that for every topological space Z, the projection map Z cross X to Z is a closed map. The second condition is X is compact. So this theorem gives you a characterization of compact spaces. So what we are going to do is employ this one both ways in proving that Cartesian product of compact spaces is compact. Of course, you have to take non-empty product and non-empty. If you take empty product, it's assumed to be a singleton or some such thing, there is no problem, but each space must be non-empty, that is important. Every non-empty product of compact spaces is compact. Okay. So the proof seems to be just a small trick, and using the principle of transfinite induction correctly, which amounts to more or less selecting appropriate notation here. Otherwise it is extremely easy proof. So I will tell you the idea and then tell you how it works in simple cases. Rest of them is just pure notations and so on. Okay. So given an indexed family of compact spaces, we want to prove that X prime is which is a product of each xi, I inside I prime, is compact. The plan is to show that for any topological space Z, the projection map Z cross X prime to Z away from X prime, okay, to the first factor. This is a closed map, and use the previous theorem. To prove this itself, we will use the principle of transfinite induction. So here is the first step, which will tell you what kind of tricks we have to do with employing principle of transfinite induction. Put a well order on the set that is important set, namely the indexing set I prime. Let us denote the least element there by 1. Okay, 1 belonging to I prime is the least element. Take any order, no problem. It must be well ordered, that's all. Extend this to a well order of I, which is disjoint union of I prime with two extra elements. I am denoting by 0 and infinity. By declaring that every element in I prime is between 0 and infinity. In other words, now 0 is the least element and infinity is the greatest element. There may be a least element here, that's always there, and that element I have written out 1. But there may not be any greatest element. So I have put a greatest element also. Okay. So this is the first trick you can say. Clearly 0 becomes the least element and infinity becomes the greatest element inside this I, which is two extra elements from I prime.
Sir,
Huh.
in the first line, we are using the well ordering principle, right?
For I
Find a
prime.
well order.
I prime.
Yeah. And now on I, you have defined a order.
Yeah.
It may not remain the well ordered set.
It is a well ordered set. Take a subset. If it contains 0, 0 is fine. If it does not contain, it will be inside. It may be containing infinity, doesn't matter. Infinity is the largest, it cannot be smallest. If you throw away infinity also, there will be a smallest element there.
Because the I prime was well ordered.
Yeah. Well ordered, we have even in the proof of using John's lemma, proof of that one we have extended this one and so on, you see. So the extensions of ordering for 1 element, 2 element, 3 elements, infinitely many elements is obvious. Okay, wherever there is infinitely many, then we have to go back to John's lemma. You have to go back to principle itself, ordering. In other words, what your objection may be that suppose I prime is well ordered and I prime is contained inside a larger set J prime. Will there be a well order on J prime which extends the well order on I prime? Even that is true. Okay. So, but we have not proved such a thing. We can, whatever proof we have given for existence of well order, you can modify it to prove such a thing also. Okay. So that is not of any use for us. I am having only 2 elements. I want it this way, not an arbitrary order. Okay, 0 is the least element and I is the infinity is the largest element. In fact, we want to work inside I prime only, but these two things help us in putting the correct notation, instead of buggy notations. That's all. Okay, now for each j inside I, let us denote the segment 0j, which means all elements strictly between 0 and j, including 0 and j. So this I will denote by capital J. Note that 0 infinity is nothing but the whole space I. Okay. Now another small trick. I want to prove that for arbitrary space Z cross x prime to x prime, where x prime is a product, that is Z cross x prime to Z, is the projection map is a closed map, right? So I want to change the notation here. Put Z equal to x naught now. And x infinity I choose another space, namely a singleton U, which is a harmless thing. Okay, it's anyway compact. This is not compact and is not supposed to be compact anyway. Okay. Now to take x to be product of all these xi's. Remember, if I only take I prime, then this x prime, that is what we wanted to prove is compact. Proving one more factor, cross with the singleton is compact, is same thing as proving the original thing is compact. So what we are going to prove is now x prime cross x infinity, which is a singleton, that is compact. Okay. Some more notation for any subset A of I. Let x suffix a denote the product of xi where I ranges over A itself. For each pair of subsets A contained inside B contained inside I, inclusion, equality allowed. Okay. Let pi be A denote the projection map from xb, B is a larger thing, to xa, which just means that drop out all the indices which are not in A. That is the projection map, right? One more simpler notation, pi of I to A will be just denoted by pi A. When the top thing is the full thing, you just write it as pi A. So that is from the whole space X to XA. Okay, these are all projection maps. Note that with this notation, xi, what is xi? It is x. Okay, and pi I is the identity map. Nothing is dropped out. All right. One more notation. Pi naught is what? It's just projection to the x naught coordinate. All right. We want to show that this is a closed map. Since x naught is arbitrary, this will prove that x prime cross x infinity, which is singleton, is compact. Now, that is the same thing as proving the x prime is compact. Okay, so this is what we want to prove. So that will prove that x prime cross infinity is compact and x prime is compact. Okay. Now the next step is, so start with a closed subset of x. Okay, you have to prove that the image is a closed set. So take a point in the closure and show that it is inside the original set pi naught of f. We want to show that this is closed. So this is equal to the closure. So I will take a point in the closure and show that it is inside. That's all. All right. Now suppose you have just two spaces. Say x is just z cross some x1. Okay. Then how do you have done this one? X projection map is compact. Okay, so the second factor is compact, projection map is closed, is what you had proved, right? So this would have been done. Similarly, for finitely many cases, we have already done the product is compact and so on. But if you don't use it, how you do that? You just reflect what you have to do, okay, successively. First you get a point in pi 1, first projection. Say suppose there are three x is z cross x1 cross x2 cross x3, let us say. So you have started with a point in x naught, which is z, right? So which is inside the closure. Take a point x naught comma x1, okay, inside pi 1 of f closure. The projection of that one to pi naught will be the same thing as this one. Next, take a point x naught, x1, x2 in pi to pi 1, 2, 1 and 2, or both of them, pi 1, 2, 3, etc. So when you take all the indexes, it is same thing as identity map, which is pi of, which is just pi I of f is just the same thing as f. F bar is f because start with a closed set. Okay, so you would have hit this one. Namely, you would have proved this one. Of course, this is a different proof I am giving you. We already know that product finitely many of them are compact. So this would have been another proof in the case of when product you have taken over a finite family, right? So once you have this idea, okay, now everything is just a set of notations and finally applying the transfinite induction. Okay, I think that makes the idea clear in the proof what is going on. All right. So start with a point x suffix top x naught, because I would like to use the lower suffix for the coordinates. Okay, this is some point in pi naught of f bar, bar denoting the closure. Okay. So for each j inside I will make a statement here Sj. Sj denotes the statement that there exists some x suffix j belonging to xj such that the xj is actually inside pi j f bar. Okay, you have to start with f, which is in the product space x, project it to this xj and take its closure. So this element must be in this closure. Then it must also satisfy that all its projections, see j prime's projection of this one agrees with xj prime. So this is an inductive or inductively xj prime denotes an element here with this property. Okay, so it must be true for xj prime also here. Xj prime belongs to pi j prime of that one. That is the inductive statement, one single statement meaning all these. Okay, so the jth projection of this one must be the same thing as the j prime projection element here, which just means that if you take the j say ith projection of xj where I is less than little j, then it must be same thing as ith projection of this element where I is actually smaller than even j prime. That is the meaning of this. The projection map, projection of these points which you are choosing next one should be the same thing as the points which you have chosen already. Okay, so this is what I did in the case of, in the illustration case. First you choose x naught and then x naught comma x1 and then x naught comma x1 comma x2. So that kind of notation is not possible. That's what I have tried like this. That's all. So this will be true for every j prime inside 0 to j. This statement makes sense even when j prime is 0. There is no problem. That x naught has been already chosen, so we know this statement is true. Otherwise it's just a statement now. Why I am making this statement? Examine the statement, okay, for S infinity. What is the meaning of the statement at S infinity? That means there is a point x suffix infinity inside x. This infinity will be now meaning 0 to infinity, which is just whole space I have told you. So x infinity will be inside x such that x infinity is inside pi infinity of f, which is again f bar, but f bar is f. So x infinity is inside f, and this one means that in particular pi naught of this x infinity is x naught. Okay, so what does that mean? That means this point is in the closure, but it is actually inside f. So we have shown that this x naught is inside pi naught of f, right? So that will complete the proof. So that is the idea of making this statement. This statement for j equal to infinity is the one which we want finally. What is the starting point? The starting point will be S1, for example. S naught is too obvious. S1 we can prove. Then we have to prove that Sj for all j by what? Obvious tricks. Namely, suppose this is true, then next one is true. That step I have to prove. That is the hardest step here. Okay. All right. So let us prove S1. Okay, this is where the induction begins. What is x1? x1 is a compact space. x0 is z. x0 cross x1 to x0 is a closed map because x1 is compact. Therefore, if you take pi 0 1, this I could have written as the square bracket also here, no problem, both of them are the same. There is nothing else between 0 and 1, by the way. So pi 0 1 f, take the closure, p of that, p is next projection, the projection, okay, that will be a closed map because this is a closed set I am taking. So p of that one will be a closed subset of z equal to x0 and contains this subset, right, p of pi of f, but that is pi naught of f. Therefore, it contains pi naught of f bar because it's a closed subset, but it contains x0. Okay, this means that you have an x1 inside x1 such that this x0 x1 belongs to pi naught bar. This proves S1. So this is why I have explained it already before. Now I am using this new notation. I have explained it. So this is the way from x1 to x2, x3 and so on we can go keep going very easily. All right. But now we want to use induction directly. So S1 is true. Now next thing to prove that, suppose for some k inside I, okay, not equal to 0, this should be 0, it's not O. Sj is true for all j less than k. All right. We want to prove that Sk is true. Why? Once we prove this, that Sj for all j less than k implies Sk is true, the condition for transfinite induction is over. That will prove that S infinity is true. So all that we have to do is Sk is true. Okay. Define y belonging to 0 to k, x 0 to k, product up till taken up to 0 k open, to be the element such that this jth coordinate of y is the jth coordinate of this xj for every j less than k. Then it follows that this yj, which is nothing but the projection pi j of 0 k. See, j is something smaller than k, right? For each j you have, for each j less than k, capital J pi j 0 k to this one of y is xj. All that you have to verify is take the ith coordinate here and ith coordinate here for I less than or equal to j, then these are the same because just projection maps they are. Okay, so that is what I have done here. For to begin with, if you take j little jth coordinate of yj, that is yj, that is the same thing as the jth coordinate of x power j, provided j prime is less than j. Okay, I should write j prime here. Then from 34, this property, okay, what do we get? With pi j prime of xj is xj prime. So this implies the jth prime coordinate of xj is equal to jth prime coordinate of this one also. Okay, for all of them. So that means that jth prime coordinate of y itself is equal to the jth prime coordinate of x power j. Okay. So I have defined what y should be. This y will be in pi of 0 k operating upon f, the closure of that. So all this is happening inside x 0 k. Okay. So we have to prove this one. We have got a y which projects correctly, but why it is in the closure? So this is where something has to be used from the product topology. What is that? The definition of product topology. That's what we are going to use. Let W be a neighborhood of y, okay, in the product topology. What does that mean? There exists a finite set I contained inside A contained inside I, and an open subset V contained inside XA. See, A is a finite set, okay, such that Y is inside V cross this X taken all the indices in the complement of A. Okay. So that is the basic neighborhood, sub-basic neighborhood. So there will be some such neighborhood contained inside V, contained inside W. Okay. Choose J to be the maximum of A. A is a finite set, okay, that's why maximum will exist, and put U equal to V cross XB contained inside XJ. Okay, now all the elements in where B is 0 to J I have taken full, okay, which are not inside A, of course. Okay, so we want to be inside this finite set, but in between there may be something. So you take J to be the maximum of A and put U equal to V cross XB. See, the V is inside, purely inside A, so I am taking 0 to J, which is a larger set. Then I take this open subset inside Xj. Then we automatically get Y belonging to U cross, what is this one? J complement is only 0k minus 0j. 0j part will be coming from U, okay. Other things are here which are full spaces, xj's. Okay, so this is anyway subspace of that one, so this will be also contained inside W. Alright, so we have got a neighborhood like this for each point y, for each neighborhood W of y, you have get such a neighborhood. These are basic neighborhoods. Therefore, what happens? What is the meaning of this one? If you take the jth projection of W, for W is inside X0k, right? That contains this subset contained inside W, so the projection will contain that one. The jth projection will contain U cross Xj. What is the jth projection of this one? All these things will go away, so it is just U. And U contains the jth projection of Y. Okay, that is how we have chosen that. First we choose only finitely many elements. Afterwards we allowed the rest of them to be free, so that the Y will come inside that. Okay, so this Y is now inside U. So that is the whole idea there. But this is nothing but Xj. Okay. From 35, we have to use this, right? Because once J is there, Y is chosen such that its jth projection is Xj. Here we have chosen jth projection is Xj for J less than k. Okay, so from 34 we know that this Xj is inside pi j f bar and U is open in Xj. It follows that U intersection pi j of f is non-empty. So this implies U intersection Xj complement, that is non-empty. Intersection with pi j, inverse of the projection map here, pi 0j to x, is non-empty, but that is contained inside W intersection the projection of f on 0 to k. So for each point, you see Y, neighborhood of Y, it intersects this one, therefore this must be in the closure of this. Okay. So this is these notations may be new to you, but this kind of thing you have proved while proving product is connected, etc. So similar argument. This is not new to you. The next step is similar to S1. What is that? We have yet to prove that, this implies the next one. So that's what. Now consider the projection pi 0 k, okay, namely for full one more element. This one more element is there, right? So capital K is 0 to k, all of them. So omit that one element, take the projection. Okay, we want to show that this is closed, but we want to use that this is closed, but that comes because this xk is compact, right? So we have to use each xk is compact after all. So because xk is compact, this is a closed subset here. The image pi k 0 k of pi k f bar, okay, that's a closed subset I am taking here, is a closed subset of 0 k, but it contains pi k of f, right? Its projection of pi k of f is there, which is nothing but pi 0 k of f, and then it contains a closure. Therefore, there exists xk belonging to xk. From here I can extend it to this one, that is the whole. One more element I can take, that is the whole idea. Xk belonging to x is that y comma xk. What is the meaning of this notation now? Which just means that the earlier projections of this element is the old y, the kth projection is xk. Okay, this is element of pi k f bar. So here I am using that xk is compact. Okay, one at a time. That step is again used here. So clearly for all j less than k, if you take the projection of this y comma xk, that will be xj. Okay, it is being same thing as projection of y. So it is xj. Okay, so this proves the statement xk, assuming that it is true, that namely for every j less than k, sk is true. That closes the transfinite induction. Over, the proof is over. So this proof is worth repeating quite often. You read it carefully. Next thing is we want to go ahead with this order topology and so on. So how far we can imitate the model, namely the real line with its order. So we go back to that and introduce a few more terminologies, all based on what we know already, what we are familiar with the real line. So let us recall the notation of least upper bound and greatest lower bound in the context of a totally ordered set. We are recalling it so that everything is devoid of all algebraic properties of real line. Only the order properties are being used. So that is why we are recalling. Emphasis is on that. So start with any totally ordered set. A subset A is said to be bounded above with respect to bounded below if there exists alpha belonging to x such that for all A inside A, we have A is less than or equal to alpha, or the other way around, is alpha is less than or equal to A. Okay, bounded above and bounded below. This alpha will be a lower bound here, this alpha is the upper bound here, the other way. In that case, alpha is called an upper bound, in the other one it is lower bound. Okay, same definition. Let A be bounded above and alpha be an upper bound. We say alpha is a least upper bound for A, or another name is supremum of A, if for every upper bound beta of A, we have alpha is less than or equal to beta. That means, first of all, the set of upper bounds must be non-empty, then you take alpha to be the least element in the set of upper bounds. For all upper bounds are bigger than alpha, so then it is called a least upper bound. It is very descriptive name. Supremum is another terminology. Exactly similarly, you can define greatest lower bound and infimum also. Okay, the notation will be inf A and sup A. Note that we have not claimed that supremum and infimum exist. Okay. However, it is easy to check that they are unique if they exist, and that is where you have to use the anti-symmetry property. That's all. In a totally ordered set, the following two conditions are equivalent. What is that? Every non-empty subset A of X which is bounded above has a least upper bound in X. Okay, that upper bound may not be an element of A in X. Every non-empty subset B of X which is bounded below has a greatest lower bound. This is just the dual of the statement. But these two are equivalent. So let us prove 1 implies 2. The proof of 2 implies 1 is just the other way around. Just you have to reverse the inequalities and so on, right? So they are similar. So 1 implies 2, if we prove, we are done. Okay, let us prove 1 implies 2. Start with a non-empty subset of X which is bounded below. Look at all the elements X, A inside X such that A is less than or equal to B for every B inside B, which just means that all the lower bounds. A is non-empty is the assumption. Okay. And because B is non-empty to begin with, A is non-empty and it is bounded above. Every element of B is bounded is their upper bound. Okay. So it is bounded above also. The set A itself is bounded above. So let S be supremum of A, which exists because X satisfies 1. Every bounded above set has a least upper bound. So that supremum is there. So this is the hypothesis 1. Now we have to conclude B, right? So this S is clearly less than or equal to B for all B inside B, because of what? We have taken the least element here. Okay. Hence, this S itself is an element here, because S is less than or equal to B. If beta is any lower bound for B, then by definition beta is inside A. Therefore, beta is less than or equal to S. Therefore, S is the greatest lower bound. This is infimum. All right. So by upper bound exists and then the supremum exists. If the lower bounded below, lower bound exists is what we have. Infimum exists what we have. 2 implies 1, as I have told you, is similar. Okay, a few more terminologies. A totally ordered set is said to be order complete if it satisfies condition 1 and hence condition 2, because they are equivalent of the above lemma. I repeat, what is the meaning of ordered complete? Every bounded above set must have least upper bound, which is same thing as saying every bounded below set has a greatest lower bound. So if that exists inside this X partial order, okay, this must be first of all a totally ordered set. Such a thing you will call a order complete. So you may be already knowing that this property we have been extensively using for the real numbers, right? So we have made it a definition here. If X is a linearly ordered finite set, then it is easy to see that it is order complete, right? Therefore, order completeness axiom is relevant only when X is infinite. Next time we shall use all these, okay, and then study order topology. So far we are not mentioning a topology at all, okay. All the time we are talking about the combinatorics of this partial ordering, total ordering, well ordering, and so on. Now the topology will enter. Okay, thank you.